Welcome back. So, we will continue with our the exercises on math preliminaries that we are doing. So, we will do some more examples to get a feel of the different notions that we have introduced, right. So, let us start with an example, right. So, for n greater than 1, let us define an interval I n as 1 upon 2 n plus 1 and any set of integers greater than 1. So, and define the set S, right, as union of n equal to 1 to infinity I n. So, we need to find S prime and the boundary of S. So, this is set of limit points of S and this is the boundary of S, right. So, let us enumerate, let us write down these sets for few values of n. So, for I n equal to 1, you have 1 by 3 and 1 by 2 and then you have 1 by 5 and 1 by 4 and so on, right. So, let us see what will be the so as n increases, right. So, this number on the left limit is decreasing, right, and so what do we get? So, S, so certainly as n increases you are approaching 0 here, right, and so even the right hand side is decreasing. So, it certainly 0 is a limit point, because about 0 you take any neighborhood around 0 or for every neighborhood around 0, right, it contains an element belonging to the set S. So, S is I 1 union I 2 so on, right, and in each of this as n goes becomes larger and larger, right. So, this approaches the value 0, right, both the left and right end points, right. So, S prime certainly consists of S because it is a union, right. So, and all these are closed sets. So, each say and S has all the all these intervals, right. So, and each of these intervals is a closed set. So, S prime will have S and also it will have the singleton 0, because 0 is also the limit point of the set S, even though it does not belong to S, right. So, what about the boundary of S? The boundary of S, right, will contain all the points, right. So, if you see here the highest number that we get is 1 by 2, right, and then if you see the pattern 1 by 2, then 1 by 3, 1 by 4, 1 by 5 and so on. So, the boundary of S consists of course, it contains the 0 also and then union 1 by 2, 1 by 3, 1 by 4 and so on, right. So, we can write this as 0 union the set 1 by n where n is greater than 2, right. So, this is the boundary of the set S. Now, we saw that we have seen how to calculate the boundary of a set. So, let us take another example and we will disprove the following statements, disprove the following statements. the first statement is boundary of, so S1 and S2 are subsets of R, and we want to disprove this following identity S1 union S2, right, is right. So, we want to disprove that, that means this is not true. So, we will have to disprove, we will have to give a counter example. So, a counter example is as follows. So, you can cook up a following example, take S1 as minus infinity minus 1 and S2 as minus 1 2, right. So, boundary of S1 will be just minus 1, because minus infinity does not belong to S1, whereas boundary of S2 consists of both minus 1 and right. And what is S1 union S2? So, it consists of all points from minus infinity to 2, right, and the boundary of S1 union S2 is 2, right. So, you see that therefore, boundary of S union boundary of S2 is not equal to boundary of S1 union S2. So, to disprove you just need to come up with a counter example. Let us take another example, and what do we want to disprove, right. So, disprove that the infinite union of closed sets is not closed, right, whereas the intersection of closed sets is closed. Arbitrary intersection of open sets is not open, whereas arbitrary union of open sets is open, right. So, in open sets also you had something to disprove, right, with an counter example, and here we will come up with a counter example with an example to show that the infinite union of closed sets is not closed. So, just we need to come up with an example. So, the set that this is the example, and the example is we take union of sets of the form 1 by n plus 1, right. So, this is a closed closed intervals or closed sets, right. So, you have arbitrary union of closed sets. Now, what happens? Say let me call this as S. So, as n approaches very large value, this number becomes closer and closer to 0, but it never becomes 0, it approaches 0. So, this will be open 0 on the left hand side, whereas on the right side you get the maximum for n equal to sorry, this should not be n plus 1, it should be 1 plus 1 by n, right. So, for n equal to 1 you get the maximum which is 2, whereas for any other value of n you get a number which is less than 2, right. So, it will take closed 2. So, what we got is the union of closed sets is a half open half closed set, right. This is not equal to the, this is not a closed set, it is called a neither closed nor open set, right. So, we have shown that the arbitrary union of closed sets is not closed. That takes us to the next notion. So, let S be a set in R, right. Let me take an example. So, let S be say minus 1 and 2. I have taken an open interval, right. Now, you can see that the number 2, right, all elements in the set S are less than the number 2. Okay. However, the number 2 does not belong to S. So, the first observation is all elements in S are less than 2, right. Why strictly less than? Because 2 does not belong to the set S and 2 does not belong to the set S. 2 does not belong to S. Same thing can be said about the number -1, right. So, there is no number, right, which is greater than it is lesser than -1, right. So, -1 is the least number in this set, okay, and again -1 does not belong to the set S. So, let us capture this in a notion called supremum of a set. So, this notion holds for only subsets of the real line, right, not subset of Rn. So, S is subset of R, right. Let us now move on to another notion that we will need frequently in our analysis, and that is the notion of a supremum of a set. So, let S be a subset of R, right, let be a bounded subset of R. A number B is called least upper bound of S, denoted by B is supremum of the set S, sup of S we call, if B satisfies the following conditions. If B satisfies the following conditions. And what is this? The first is B is an upper bound for the set S. It has to be an upper bound, right. Second is no number less than B is an upper bound for S. So, if you can find a number B which satisfies these two properties, that is B is the least upper bound for S and no number less than B is an upper bound for S, then B is said to be the supremum of the set S, right. So, to give an example, take S to be say -1, 2, it is a bounded set in the real line, right. So, the upper bound is 2 because there is no number which is lesser than B and forms an upper bound for the set S, right. So, here in this case B is supremum of the set S, right. So, it satisfies both this, as I said, 2 is it satisfies the first condition, it is an upper bound for the set S because all numbers are less than 2, and the second condition also holds, there is no number other than 2 which satisfies the upper bound condition. Okay. Note that what differentiates this between the notion of maximum value of a set and the supremum is that supremum of a set need not belong to the set. So, in this case you can see that here which is 2 does not belong to S. So, a number can be a supremum of the set even if it does not belong to the set S. Right. So, similarly one can define the notion of infimum of a set, infimum of a set, right. So, again let S be a bounded set in R, a number say A is said to be the greatest lower bound. So, unlike in the supremum you had the least upper bound. So, we have here the greatest lower bound for the set S denoted by infimum of S, right, if A satisfies the following conditions. And what is that? A is a lower bound for S. Second is no number, unlike here there was no number less, here no number greater than A is a lower bound for S. So, the same example, we took the example as -1 and 2 open interval. So, this is here the infimum of S is -1 and this number does not again belong to the set S, right, because that is the lowest bound for the set S, right. There is no number greater than -1 which is a lower bound for the set S. So, again here as I said the number -1 does not belong to set S. So, the infimum of a set need not necessarily belong to the set S, right. So, let us take some more examples to illustrate the notion of supremum and infimum, right. So, I have a set S which is set of points such that x square is less than. Again this is a bounded set in R, right. So, we can write x square minus 9 less than 0 which implies x plus 3 x minus 3 is less than 0. So, it implies this has to be positive and this term has to be negative, x plus 3 has to be positive and x minus 3 has to be negative, which implies x is greater than minus 3 and x is less than 3, right. Together this implies that x is greater than minus 3, but less than 3. So, the set S consists of all x which satisfies this inequality, right. Therefore, the set S is upper bounded, the least upper bound for the set S is 3 and the infimum of S is minus 3 and both do not belong to the set S. Another example, suppose S was minus 1 2 with the open on the right side. So, this is again a bounded set. So, the supremum of S is 2 which does not belong to the set S, whereas the infimum of the set S is minus 1, which belongs to the set S, right. In fact, we say the infimum is achieved, right. So, that is the minimum element. So, we talk about max and min when the elements belong to the set, right, but if they do not belong, we use the word supremum and infimum accordingly. But we will take one more example. So, S is set of points such that the absolute value of 2x plus 1 is less than 5, right. So, x belongs to S implies 2x plus 1 is less than 5 and also minus of 2x plus 1 is less than 5. So, if you do further simplification, this implies x is less than 2, but greater than minus 3, right. So, again the supremum of S is 2, which does not belong to the set S, and the infimum of S is minus 3, which again does not belong to the set S, right. So, that brings us to the notion of supremum and infimum. We move on to one more notion, that is the notion of continuity of a function. So, let f be a real valued function, right. So, real valued function. So, you might have been familiar with the notion of continuity using the notion of limits, by using the notion of left limit, right limit. So, when both are equal, when both the limits exist and they are equal, we say that f is said to be continuous at that point. But let us not use the basic the calculus approach, but we will do it more from the from the point set topology notions that we have discussed so far in this course, right. So, definition: f is said to be continuous at a point if given any epsilon greater than 0. So, an epsilon is like a challenge thrown to you, and if you can come up with, given any x belong to a b, continuity at x, if given any epsilon greater than 0, there exists a delta greater than 0 such that the following holds. What is that? F of x, right, belongs to a ball with center x and radius epsilon whenever x belongs to a ball with center x and we next move on to the notion of continuous function, right. So, let f be a function, a real valued function. We say f is continuous at x belong to a b if given any epsilon, if given epsilon greater than 0 there exists a number delta greater than 0 such that whenever norm of x minus y is less than delta implies norm of f of x minus f of y is less than epsilon. So, what this definition says is that let us picturize this, right. So, you have the real space, right, it is mapping from an interval in the so I can even talk about instead of an interval I can take a function from R to R, right, and let us now move on to the notion of continuity, right, of a function. So, let f be a mapping from R to R, right. We say f is continuous at x belonging to R if given epsilon greater than 0 is like a challenge thrown to you, there exists delta another number greater than 0 such that whenever norm of x minus y is less than delta implies norm of f of x minus f of y is less than epsilon. Of course, here you can replace the norm by absolute value because we are from real line to real line, but this definition holds for in general from mapping from Rn to Rn space. So, we say that f is continuous at a point x if given epsilon greater than 0, somebody gives you an epsilon and you come up with a number delta such that for all y which are in a delta ball around x, the function f of x lies in a ball of radius epsilon centered at f of x. So, let us picturize this. So, you have a x here, you have a delta ball, right, and then you map all this through this function f, you end up with a ball with center as f x and radius as epsilon. So, f is said to be continuous at x, right, if this is given to you, epsilon is given to you, right, x is a test point and epsilon is given to you. If you can come up with a delta, a number, a positive number such that for all y in this ball, open ball, right, note that this is an open ball because this is a strict inequality, for all y in an open ball with center as x and radius delta, the function gets mapped to, so there is a f of x sitting here and then all other points map to f of y. And how do they map? Well, they all lie in a ball with center as f x and radius as epsilon. So, if you can show for any epsilon that is thrown out to you, if you can find out a delta such that this inequality holds, then f is said to be continuous at x. If it holds for every point in the real line, then f is said to be continuous over the real line, right. If f is continuous at every point in R, then f is said to be continuous over the real line, right. So, you can replace the real line by subsets of R, by intervals, closed intervals and so on. So, once we have the notion of continuity, we can define the notion of path simply connected set. So, we already saw the notion of connected set. Connected set roughly captures a set is in one piece, right. We said that we define connectedness by defining the notion of a set being separated. So, two sets A and B are said to be separated if if A union B is the whole space, and if A intersection B closure is null set and A closure intersection B is also null set. So, we say that A and B are said to be separated. If they are not separated, then they are said to be connected. Once we know the definition of connected, we need a notion of simply connected. So, this notion of simply connected is useful when we talk about non-existence of periodic solutions, right. So, for that we need so we already defined the notion of continuity. So, let us define two more notions, that is a curve. A curve in a subset X of Rn is said to be is nothing but a continuous function from an interval a b to the set X, right. So, once you have the notion of curve, we say a curve is closed if the start and end points coincide, right. So, a curve is a curve or a loop is a closed curve or loop is such that the start point of the curve and the end point of the curve are the same. So, here we have examples of closed curves, and these are just curves, right. These are not closed. So, once we have this notion of loops or closed curves, we can define the notion of simply connected set, right. So, a set S is called simply connected if it is connected, that is the first requirement, and every loop gamma in S can be continuously shrunk to a point in the set, right. So, more mathematically, if there exists a continuous function g which maps from the interval a b Cartesian product 0 1 to the set S such that g at 0 is the curve gamma and g at x comma 1, that is at when it takes the upper limit of this set 1, g of x 1 is the point, the singleton set, that is the point A, where A belongs to set, right. So, note that there are three important things in this definition. One is the set has to be connected, right. Then you have to come up with a function which is continuous, a function g which is continuous. So, what it does? It takes loops and shrinks it to a point belonging to the set S, right. So, this is also one of the key things to remember, that you should be able to shrink it to a point, but that point should belong to the set S, right. So, it is easy to visualize now with this definition what is meant by a not simply connected set, right. So, a set with a hole, right, like the annular region, right. So, a set like this where it contains all these shaded points, but not the unshaded point. So, this is an annular region. So, the annular region is not a simply connected set, because no matter what closed curve you take, right, you will never be able to find out a continuous function which shrinks this curve to a point belonging to a set, right. So, this is as I said, this is going to be, this notion of simply connected set is going to be used when we talk about periodic solutions, right. So, we will end this lecture on the math preliminaries, right. Thank you.